In this video, we will be looking at the concept of called a parameter of a probability distribution. By the end of this video, you should be able to define what a parameter of a probability distribution is, and you should also be able to define a family of probability distributions. Let us consider two Bernoulli probability distribution examples, or Bernoulli random variables. So the first example looks at an experiment where we want to observe whether a student will pass or fail a test. And so the additional information that's given is that there's a 60% chance that a student, randomly selected student, would pass the test or an assignment. And we can then also define a random variable x as follows. So we could say let random variable x indicate whether a student would pass the test or not. And so because we have only two possible outcomes, a student passing or failing, then it means that our sample space will be made up of these two outcomes, either a pass P or a fail F. We can also let the outcome P be denoted by numerical value 1, and we can also let the outcome F be denoted by numerical value 0. And so the possible values for our random variable x is given as 0 and 1. And by definition, this is a Bernoulli random variable since we only have possible values 0 or 1, 0 and 1. And so random variable x follows a Bernoulli probability distribution. Alright, so from this information that there's a 60% chance of passing, we can define our PMF, or probability distribution. So we can define it using a table. And so in this case, we have the first column indicating the possible values of our random variable, which is 0 and 1. And we have the probability of observing each of these possible values. So the probability of x equal to 0 is equivalent to the probability that a student would fail the assignment or the test. And so using the given information, we could say that P0 is equal to 0.4. And P1, probability that x is equal to 1, is equivalent to the probability that a student would pass the test or the assignment. And so that probability is 0.6. Now the total probability here, it would add up or should add up to total probability of 1. Good. So we see that yes, this is a valid PMF. This whole entire table defines the PMF or probability distribution. And so yes, it's a valid PMF since both probabilities, the greater equal to 0, the positive, and the total, or they add up to a total probability of 1. Now, if we then represent our PMF using a formula, we'll start with writing Px equal to, and in curly brackets, the probabilities of if you observe x equal to 0, if you observe x equal to 1, and otherwise. And this otherwise is all other possible values of random variable x where they're not equal to 0 or 1. And so we see that the probability, if we start here, probability of x equal to 0, it's given as 0.4. Probability that a student would pass the test or assignment, it's given as 0.6. And the probability that x is equal to 2 or 3 or 16 or 8 or 2.5 or something like that is equal to 0. All right, so from just this information, we can define the PMF of a Bernoulli probability distribution. Let us then consider the second experiment. In the second experiment, we would like to observe whether a student would complete or finish their BSc degree in 3 years or not. And we can define a random variable x as follows. So you could say let random variable x indicate whether a student completes the degree in 3 years or not. And we have additional information that says there's a 33% chance of completing a degree in 3 years' time. And so since we only have two outcomes, it's yes, they've completed in 3 years' time, or no, they haven't, our sample space will be made up of only these two possible outcomes. So either one of them would be true. We can also let the outcome yes be denoted by numerical value 1 and the outcome no be denoted by numerical value 0. And so the possible values for our random variable x is 0 and 1. So this proves that we have a Bernoulli random variable since we only have possible values 0 or 1 for our random variable x. Right, so if we then define our PMF using a table, we will start by drawing our two columns, with the first column indicating the possible values of our random variable x, and the second column indicating the probability of observing those specific possible values. So we see that from the given information, the probability that x is equal to 0, meaning the probability that a student would not complete in 3 years' time, is given as 0.67, right? So it's 1 minus 0.33. And the probability of observing x equal to 1, that's the probability that a student will complete in 3 years' time. Then we see that the probability is 0.33. Now the total probability here should add up to 1. And yes, it does. 0.67 plus 0.33 adds up to total probability of 1. So this is a valid PMF. Now if we represent or define our PMF using a formula, then we'll write Px is equal to, and in curly brackets, the probability of x equal to 0, which is given as 0.67, and the probability that x equal to 1, given as 0.33. And if you have any other x value, that probability there is 0. So we see that for both examples of a Bernoulli random variable, the PMF has a similar structure. So they both have similar structure. And we see that the only information that was actually necessary for us to complete a PMF was that only original information that was given. 60% chance of passing, 33% chance of completing a degree. So if we have that single point or information, then we can complete the rest of the PMF. Since we have two possible outcomes, 0 or 1, we know that the probability of both, of observing one of the possible values of x is equal to 1 minus the probability of observing the other one, right? So if we have the probability of one outcome, it means that you automatically have the probability of the other outcome. Since there could only be two outcomes for a Bernoulli random variable, it's either a yes or a no, true or false, or x equal to 0 or x is equal to 1. So if we have the probability of x is equal to 0, then for sure you will know how to calculate the probability of x is equal to 1, right? Since the total probability, if we add up the two probabilities for x equal to 0 or x equal to 1, they must add up to 1. So if you have one of these probabilities, then the probability of observing the other possible value is equal to 1 minus the probability that you have there. So in this case, or with both of these examples, we see that the only information that was actually necessary was that given information there, 60% chance of passing, which means that already we know that there's a probability of 0.4 of failing, right? If we have a 0.6 of passing. And then with the second experiment as well, we're given information that there's a 33% chance of completing. And so from this information, we can define the whole PMF by just using the single information. Since we know that probability of observing x equal to 0 is 0.33, it means then the probability of observing x equal to 0, that will be 1 minus 0.33. All right, let me say that again. The probability from this single information, they let us know that there's a 33% chance of completing a degree in 3 years' time. So it means that the probability of x equal to 1, that is equal to 0.33. And so since we have this information, we automatically would have the information or the probability of observing x equal to 0, right? So since we only have two possible outcomes, 0 or 1, it means that the probability that x is equal to 0 will then be equal to 1 minus 0.33. In this case, is 0.67. All right, so the whole idea here is that if you have single information or the probability of one of the possible values, then it means that you have the probability of the other possible value. And it's only in the context of a Bernoulli random variable because we only have two possible outcomes only. So this then leads to the general form of a PMF of a Bernoulli random variable. And so we can denote this probability of observing x equal to 1, or probability for observing x equal to 1, using a quantity called a parameter. And most of the time you will denote a parameter using some Greek letters. So you could use Greek letter alpha or beta or tau. But in this textbook and chapter, for Bernoulli random variable, we will use the parameter alpha. And so it says that the general form of a PMF for Bernoulli random variable is given by Px. So it's Px with parameter alpha. And so it says that the probability of observing x equal to 1 is equal to alpha. And so if we have that information, we would already know what the probability of x equal to 0 is. And that is just 1 minus alpha. So this is the general form of a PMF of a Bernoulli random variable. So it says there that every probability distribution for a Bernoulli random variable has the form expression of 3.1. And so each probability distribution will be a member of a family of Bernoulli distributions. Meaning here, if we have the first PMF, the PMF of the first experimental example, we can see that our alpha here is equal to 0.6. And so 1 minus alpha here is equal to 0.4. In the second experiment, we see that alpha is equal to 0.33. And so 1 minus alpha here is equal to 0.67. All right, so then it says there that the quantity alpha in expression 3.1 is a parameter, and each different value of alpha must be between 0 and 1 in this context. Each different value of alpha will determine a different PMF, right? And we'll say that it will determine a different member of a family of distributions. So one of or two examples of members is these examples here, where alpha is 0.6 here, and for this example, alpha is equal to 0.5. So if we have the parameter, if we have alpha, or the value of alpha, that means that you can calculate the probability of the other possible values of a random variable. So every probability distribution for a Bernoulli random variable has the form expression 3.1. And so it is called the family of Bernoulli distributions. So all of these PMFs, the different ones, each one is a member, and together they form a family, or all of them, they form a family. Now, the final definition of a parameter says, suppose a probability distribution function Px depends on a quantity. We see that it's alpha, or it could be beta or tau or any other Greek letter. But this quantity or parameter should take on a numerical value. Okay, so the definition says, suppose Px depends on a quantity that can be assigned any one of a number of possible values. Alpha, any number between 0 and 1, for example, with each different value determining a different probability distribution. Okay, such a quantity is called a parameter of a distribution, and the collection of all probability distributions for different values of the parameter is called a family of probability distributions. So you have now learned the concept of a parameter of a probability distribution.